Found it. Okay, so let's begin. So I'll start with Eisenstein criteria, which was not covered in the regular lectures, and then move on to modules. Okay. So let's recall. I suppose some of you may have seen Eisenstein criteria before, at least over integers. So let me just cite this version, and essentially the same version holds in slight generality. So whenever the proof works, you just say that's it. Yeah. So that's the setup you can generalize to. So let fx be a monic polynomial, so given by x power n plus an minus 1, x power n minus 1 up to a0. And p be a prime number, since we are talking about zx. So the coefficients are integers, ai's are integers, and p is some prime number in integers, such that p divides all these coefficients a0 to an minus 1, and p square, so this is 2, p square does not divide a0. Then you can conclude that fx is irreducible polynomial. So we'll see some examples. Yeah, I mean, of course, one can write such polynomials very easily, which satisfies this condition, and immediately you'll get that this is an irreducible polynomial. Yeah, using this criteria. So the proof is not very difficult. So we prove by a contradiction. So suppose you have a polynomial satisfying this criteria for some prime p, then and suppose that you can write fx as gx times hx. So gx is x power m plus bm minus 1 x power m minus 1 up to b0, and hx is this polynomial. So of course you can make sure gx and hx are monic, yeah, because the product has to be monic. So even if gx is not monic, its leading term has to be a unit. Yeah? So you divide by the unit and assume that this is just for simplicity. Okay, so you can assume that gx and hx are monic. Okay, and since we are assuming that fx is reducible, both m and l are less than n. Yeah, it can't happen that m is equal to n, because then l will be forced to be 0. Yeah, and hx will be 1. So that is not the scenario. Both ml are are strictly positive integer, and hence less than n, because the sum is equal to n. Yeah. So from the hypothesis, we know that p divides a0. Yeah, and a0 is same as is the constant term. And how do you get the constant term? By multiplying g and h. Just multiply the constant terms of g and h. So p divides a0, which is same as b0 times c0. But p is a prime number, so that tells you that p has to divide b0 or p has to divide c0. Yeah. So we may assume one of this holds. So we can assume p divides b0. Yeah. Otherwise you interchange g and h, or you write the two cases. Yeah. Either way. So we can assume p divides b0, and then what you do, p divides b0. So you from b0 you can start going backwards. So maybe p also divides b1, or p divides b2, and so on. So let I0 be the smallest integer such that p does not divide bi0. Yeah. So I0 could happen. So bm by convention is 1. Yeah. So bm is 1. Okay. Bm minus 1 is something. Since this is a monic polynomial, bm is 1. Yeah. So of course I0 has to be less equal m. Yeah. Because you can't go. I mean, of course, p can't divide 1. Yeah, so it's not going to go to infinity or something. It's a finite number. Yeah, and so I0 is some number between m and I guess 1, because it can't be 0. I0 can't be 0. Yeah. So now we look at AI0. Yeah, what is the coefficient, which is the coefficient of x power I0, yeah, in fx, ai0. So what is ai0? So you try to multiply this. So how, when you multiply it, g and h, where g is given by this polynomial, and h is given by this polynomial. So if you try to multiply it, you'll get bi0 c0 plus bi0 minus 1 c1, and so on. bi0 minus 2 c2, and so on, up to b0 ci0. Yeah. And the assumption that p divides I0 is the smallest integer such that p does not divide bi0, that tells you that bi0 minus 1 will be divisible by p, bi0 minus 2 will be divisible by p, and so on up to b0 will be divisible by p. Yeah. So in this right hand side, all the term except the first term is divisible by p, so their sum is divisible by p. And of course, p divides ai0 because that is the hypothesis. Yeah? P divides ai for all I between 1 and n minus 1. And I0 is less equal m, which is strictly less than n, and hence p divides ai0. Yeah. So that tells you that p has to divide bi0 times c0. And and since p does not divide bi0, it tells you that p has to divide c0. So this is since we are assuming that p does not divide. So that is the definition of I0. Yeah. Okay, I'm sorry. So it's moving a bit too much. Since p does not divide bi0, yeah, it has to divide c0. But then p divides b0. That was our assumption, and so we are assuming p divides b0, and it also divides c0. So that will tell you that p square divides a0. Yeah, and that contradicts the hypothesis. So we are assuming that p square does not divide a0. Yeah. Hence, of course, you can't factor fx like this, dx times hx, which means fx is irreducible. Excuse me. Okay, any questions? Okay. So in the, as I said, the proof is fairly simple, and you can see that we haven't used much. What we have used is that p is a prime, yeah, satisfying this property. Yeah, so this you can easily generalize. You can replace z by any integral domain, and fx is some polynomial with coefficients in that integral domain, and p is some prime number. So instead of prime number, you have to take a prime element. Yeah. If R is in particular UFD, you can say that P is an irreducible as well, because irreducible and primes are same. But this you can generalize to any integral domain. Yeah. So let me just write a general more abstract version. So, and the proof is same. Yeah. So I to write it in red. Generalized version. Let R be an integral domain. Okay. And P in R be a prime element. Let fx equals x power n plus en minus 1 x power n minus 1. So again, even in this, you don't really need fx to be monic. As long as the leading coefficient is unit, it's okay. Yeah. Anyway, up as irreducibility is decided up to associate. Yeah. be such that P divides AI for all I, or you can write it as AI belongs to the ideal generated by P. So okay. Anyways, and P square, all I meaning all I in this list, yeah. So 0 and then -1, and P square does not divide A0, then Fx. So this is in so somehow this touch screen is acting weird. Belongs to Rx, and then Fx is irreducible. Okay, so that's the generalized version. And as I said, the proof is basically the same. You just repeat the proof. Okay, so let's see some examples and then we'll go into exact sequences and stuff. So example. So for instance, you take x power so x power 5 minus 7x squared plus 49x plus 14. Yeah, so this is a polynomial which will be irreducible. You take p to be 7. Yeah. So it's the good thing about this criteria is easy to verify. Yeah. So this is irreducible in ZX, and is it irreducible in QX?
Yes, sir.
Yeah, because it has content 1. Yeah, it's a monic polynomial. So it's so Gauss lemma tells us that if it's irreducible in ZX, it has to be irreducible in QX as well. Okay, nice if and only if in fact. Then you can write a polynomial in two variables in let's say QXY. And y cube plus x square y plus y square plus xy plus x cube minus x. Yeah. So is this irreducible?
Yes.
Yeah. So what is the prime here?
X.
X. Yeah. So you can check that. My volume is turned down. Yeah. So you can check that X is the. So you can check that the constant term here is divisible by X and not by X square, and all the intermediate guys are divisible by X. Yeah. So this is irreducible. Take P to be X. Okay. So there is, so sometimes it's sort of from the polynomial you can figure it out. So sometimes you can still decide it, though even if it doesn't look like this. So for instance, you can look at
Sir,
yeah.
sir, in 2, this coefficient of y is x.
Yeah. So
So constant intermediate terms all are not divisible by x square, right?
are divisible by x. You need only divisible by p, right? The condition is all the ai should be divisible by p,
Yeah.
and the constant term shouldn't be divisible by p square. Okay. So here all of them are divisible by x, and the constant term, which is x cubed minus x, is divisible by x but not by x square. Yeah. So that's all it counts. Okay. So maybe I'll, so there you can look up more exercises and stuff from Dummett and Foote based on Eisenstein criteria. You'll see many more examples. Yeah. So one is, you know that this polynomial x power p minus 1, yeah? Is this irreducible in let's say zx? I don't know. It's frozen. Okay. Let me see. Is this irreducible?
No.
This is obviously not irreducible, right? We know one of the factors, which is x minus 1. Yeah, so this is same as x minus 1 times something. What is that something? X power p minus 1 plus x power p minus 2 x plus 1. Yeah, so so you can check that if you multiply this through, you'll get this. Yeah. What about the second factor? Is this reduce? So here p is a prime. Yeah. So is this reducible?
No, sir.
No, sir.
How do you know?
X plus 1 or x minus 1 substitution. We have to
No. Can you factor the second factor further?
No, sir.
So it is irreducible, right?
Yeah.
That's what you're trying to say. Yeah, sorry. So I asked, is this irreducible? And someone said yes. That's so it is irreducible. Yeah. So you have to check why it is irreducible. So as you can see, I mean, all the coefficients are 1. Yeah. So immediately you can't apply this Eisenstein criteria immediately. So you have to do some change of variable. Yeah, and then it becomes irreducible. Okay. So, so what is that change of variable?
X plus.
So maybe I'll write y as x minus 1. Yeah. So, so this polynomial, the second factor, let's call it fx. Yeah. So the second factor, just the second factor. Yeah. So maybe I'll write it here is fx. Okay. So now fx will be reducible if and only if I make this transformation and that new polynomial, which maybe I'll call it gy, if gy is reducible. Yeah. So the y equals x minus 1, that tells you that x is y plus 1. Yeah. So fx is same as fy plus 1. So if fx is reducible, fy plus 1 is reducible, which is a polynomial in y and with coefficients in z. Yeah, and it's easy, and then one can check whether it is irreducible or not. Yeah, so if this polynomial in y is irreducible, then you know fx is going to be reducible. So what is fy plus 1? So um, so we are doing this x minus 1, we are setting it to y, yeah, or x we are setting it to y plus 1. So this becomes y plus 1 whole power p minus 1 divided by x minus 1, yeah, which is same as y. Yeah, so this is what fy plus 1 is. Right? I'm just rewriting it in a different way. Yeah, fx is x power p minus 1 over x minus 1. So that is what I've written. So now you try to work this out, use the binomial theorem or whatever. So what you get is y power p plus p y power p minus 1 plus some binomial coefficients will be there. And at the end, you'll get py plus 1 minus, so that is the expansion of y plus 1 whole power p, and then there will be minus 1 and then divided by y. Yeah, so you can see this is same as y power p plus p y power, and then okay, maybe I'm belaboring it a bit, but okay, it's okay. P choose 2 y power p minus 2 dot 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 uh, p choose p minus 1 if you like. No, p minus 2, p choose p minus 1 is p, yeah, y square plus py over y, yeah. So you cancel this y and this y goes away, this becomes 1, and this becomes minus 1, this becomes minus 2, this becomes minus 3, yeah, and so on. So now you can apply Eisenstein criteria. With um, p as the prime. Yeah. So you can see that all these binomial coefficients are divisible by p. Yeah, p being a prime, and of course p square does not divide the constant term. So that tells you that fy plus 1 is irreducible, which means fx is irreducible. Okay. So this is one of the applications application of Eisenstein criteria. So I mean this may look a bit tricky, but there is some science to it in some sense. Meaning, so when you learn some number theory, you will realize there is something called ramification. Yeah. So you will see that. So I'll just use the words without explaining it. But of course, the proof as it is clear to you. So what happens is, if you take some polynomial in Zx, then you say that it is an Eisenstein polynomial for some prime p if this if it satisfies this Eisenstein criteria for that prime p, and this one can check more intrinsically by so what you do is you adjoin some root of this polynomial and you get a bigger field, yeah, a field extension of Q. And you look at what is called ring of integers of this field. So which is called something called, so which is basically integral closure of C in that bigger field. And then one studies ramification. Okay, so maybe this is a bit too much. So then what you can see is that the prime p which you chose is what is called is totally ramified in this field extension. Okay, if it was a root of a Eisenstein polynomial, and this is in fact characterizing property of Eisenstein polynomials. Eisenstein extension. So if you have a field extension such that some prime is field extension of Q such that some prime is totally ramified, then that field extension is generated by a element whose whose minimal polynomial is a Eisenstein polynomial for that prime P. Okay, so both directions are true. But let's not worry about it. So these were some applications of Eisenstein criteria. Okay. So this is all I wanted to say about Eisenstein criteria. So let me get to this complexes and exact sequence of modules. Okay. Are there any questions before I move on?
Excuse me, sir.
Yes.
Yes, sir. So you were speaking about ramification and the existence of a polynomial which is Eisenstein, which generates that extension.
Mm-hmm.
So can we think of, like, if we just consider ZX, not the extensions as such, what can we say about the density or or how? Of course, we can't say how many, like there are infinitely many, but about the density or the behavior of Eisenstein polynomials, or some polynomial which can be changed into an Eisenstein polynomial in that field.
So I'm not sure what your exact question is, but so there are extensions which are not Eisenstein, yeah, of GX, and even if there is an extension which is Eisenstein, there may be yeah, so it may be given by various. So you can write. So you have to choose the right polynomial. Okay. So it's not clear that. So you can take, it's generated by many elements, and some of them the minimal polynomial may not be Eisenstein. Okay.
Yes, sir.
So for instance, here's mu(n). So if you take a random element, it's unlikely to be Eisenstein.
Yes, sir.
Okay.
So yes, sir. That was my question. As in, we know that like if we only consider the derivative, how many of them are Eisenstein? That's pretty less.
Yeah. So it is not dense. It may, I don't know, dense or not, but it is somewhat special. Yeah. So it's not a generic situation. Okay.
Yes, sir. So that's what my question was. Thank you, sir.
Sir?
Yes.
So is there any way to determine if some polynomial can be converted to a Eisenstein polynomial by some translation?
Yeah, so that is what I was trying to say. So that requires studying ramification theory and all. Yeah. So once you adjoin the root, you get you adjoin the root of that polynomial, and then you have to study this field extension and see what are the primes which are ramified and how they are ramified. So if you find a prime which is totally ramified, then that says that you should be able to do it. Okay.
It's like we study that in number theory.
So it is something in number theory. I'm not sure you will find it in the first course in algebraic number theory, but yeah, it is part of number theory. Yeah. So maybe you can look up online and see if you understand the arguments. Okay. But of course, the basics of this you will certainly study. So some ramification theory and some number fields, etc. You will study in number theory. So the base will be ready. I'm not sure if the Eisenstein polynomials may not be discussed. Okay.
Thank you.
Any other questions? Okay. So let's get to modules. Okay. So first I want to define this complex of exact sequence, complex and exact sequence of modules. So we have a ring. So R is a ring, and F and G are two R module homomorphisms. Yeah. The sequence F, the sequence of module these two maps, A to B and B to C, is called a complex if so A to B, remember, is this map F. So why things are written somehow this not work, this pen is not working very well. So so A to B and B to C are these morphisms F and G, and we say that this is a complex if image of F is contained in the kernel of G. Okay, and you say that the sequence is exact if image of F is exactly equal to kernel of G. Okay, so another way to check image of F is contained in kernel of G. Yeah, so this is slightly easier to check. This happens if and only if you compose these two maps. So first apply F and then apply G. This should be the zero map. Zero map. So if this is zero map, what it says is that whatever lies in the image of F, so you take F of something, F of A, then if you apply G, then it must become zero. That is what image of F contained in kernel of G means. Yeah. So if you think about it, this is obvious. Okay. Make sense, everyone?
Yes, sir.
Yeah, so we'll see some examples in a bit, but so this is so complexes we won't study much, but so this we won't study much, but this one exactness we'll study a little bit. So, but their complexes are important as well, but maybe in a later course you'll study. So. Lot I mean it's a slight generalization, yeah. So you study in general, what you get is a so if you do something to an exact sequence or something, you get a complex, and then you want to check whether it's is exact or not, or yeah. So in topology, etc., also complexes are important, so you should know this concept. But so when you try to compute something called cohomology and stuff, or homology or cohomology, people start by writing a sequence of maps, which in general is just a complex. That means composition of two consecutive maps is zero. And then you try to figure out how far it is from being exact. Okay, that is what homology and cohomology is about. But okay, so let me just write down some examples before saying more about it. Yeah? So this is what. So what's an example of a exact sequence? Okay. So for instance, so I have to write 3-term sequence. So I take Z. So R, maybe R will be Z, and Z square, and Z. Yeah. So is this exact?
So we can find an inclusion and quotient.
Yeah, so one has, so I haven't told you the full information. Yeah, so at one has to find, one has to say what these maps are, then only you can answer this question. So, so you can take X going to, N going to, more suggestively, N going to N comma 0, and this is the first map. And the second map is N comma M going to, let's say, M. Yeah. So the this is the first map is injective, and second map is actually surjective. But that is not important. What we have to check is whether the image of F is same as the kernel of G or not. Yeah. So you take image of F. What is image of F? That's N comma 0, N in Z. Yeah. So think of it as equals 0. And kernel of G is also precisely the same thing. Yeah. So You want those elements which will map to 0 by G. And then the only way that's possible is if M is 0. Yeah, so this is same as this case. Yeah, it's the same as this. Okay, so is this is exact. Yeah. Okay. So in fact, this is better than exact. Yeah. So so there is something called a short exact sequence. Yeah. So or maybe before going there, let me just write a few more examples. So let R be a ring. So and F from M to N be an R module homomorphism. Yeah. So we can cook up some exact sequences out of this. Yeah. One way to cook up is, so F is a R module homomorphism. You can look at K, you can declare K to be kernel of F. Yeah. Then of course you have a map I from, so I'll write it this way. You have a map from K to M, yeah, which is I, kernel of F. And its image is precisely K, because it's the inclusion map. If you compose it with F, it will become 0. Yeah. So this is certainly a complex, but in fact it is exact because by definition, kernel of F is same as the image of I. Yeah. So this is exact. Okay. So and second thing is that this exact sequences is not, it need not be just a 3-term sequence. Yeah. So this is the base case. So so more generally, if you have a sequence of maps, so let A1 R be a ring. F1 A2 to A3, let's call that map F3 and so on. So maybe up goes till AN. So AN plus 1. Yeah, so maybe we'll stop here. Fn. Yeah, so say this should be F2 and this should be F3. Yeah, now the induction is fine. So be a sequence of R modules. It is said to be exact at, let's say, a k for some k less than equal to n, if and greater than equal to 2. So maybe I'll just k between 2 and n. If what? So if I want to decide at A2, then kernel of F2 should be same as image of F1. Yeah. If kernel of Fk is equal to image of Fk minus 1. Okay, so so if it is and you say that this sequence is a complex, if the successive compositions are 0, or image of F1 is contained, image of Fk minus 1 is contained in kernel of Fk, and you say it is exact at Ak, if this happens, and you say that the sequence is exact if this holds for all of them. We say the sequence is exact if the above is true for all k between 2 and n. So at every point, image is same as the kernel, then you say that the sequence is exact. Okay. Does that make sense? Any questions? Okay, maybe I wrote a little too much. Okay. I hope this is still visible. Okay, so again, continuing with this example 2. So we saw that this is a short exact sequence. We can this is an exact sequence. Okay, maybe I'll introduce this terminology as well before going to this example. Further talking about example 2. So a sequence of R modules, R module homomorphism uh, 0 to A to B to C to 0 is said to be short exact sequence. A sequence of R module homomorphism which of this kind. Yeah, so to be a short exact sequence. If so, maybe this is F, this is G. There is only one way to give a map from the 0 module to A. Yeah, 0 has to go to 0, and there is only one way to give a map from C to the 0 module, which is send everything to 0. Yeah, so I don't have to write what these two maps are. If this is exact, if this sequence is exact. So short exact sequence is a 5-term exact sequence where the first term is 0 and the last term is 0. Okay, that's what short exact sequence means. So this is important because even the larger sequences of modules you can sort of study using short exact sequences. So somehow a lot of information is captured just in this 5-term sequence. And you can reduce a lot of study of exact sequences to these 5-term sequences. That's why this gets a special name. Okay, so this is a short exact sequence, and yeah. So let me just elaborate a little bit about this. So what does this mean? So this is a short exact sequence. So in this case, what can we say about F?
Injective.
Yeah, because the kernel has to be same as image, and the image has to be 0. Yeah, so F is injective since it's a short exact sequence, and G is
Surjective.
surjective. Yeah, and we also know since it's exact, this means that also image F is equal to kernel G. Okay. So saying that a sequence of two maps constitute a short exact sequence. So a sequence of two maps F and G constitute a short exact sequence precisely means, first of all implies that F is injective, G is surjective, and image F is equal to kernel G. In fact, the converse is true as well. So it precisely means this, yeah, that the first map has to be injective, the second map has to be surjective, and the image of the first map should be same as the kernel of the second. This is what, so if you are given two maps with these three properties, that means you can write a short exact sequence. And if you are given a short exact sequence, it means precisely this. So in particular, in example one, this F and G forms will lead to a short exact sequence, because F was injective and G was surjective. Okay. So now getting back to this problem 2. Okay. So if F is surjective R module homomorphism from M to N. So this is from M to N. Then what we can say is this exact sequence we have written, K, M, N. So this was I, this was F. So another way to write a surjective R module homomorphism is to say that this is a short exact sequence. So this is just a tautology, right? So if this is surjective, then of course, so we already checked that image of I is same as the kernel of F, more or less by definition. I is injective map, so this it's exact here, and F is surjective by assumption, so this is exact here. Yeah, so this is indeed a short exact sequence. And if this was a short exact sequence, then F is a surjective R module homomorphism is also clear. Yeah. And so there is so if F is there is a similar way to encode injective R module homomorphism in terms of short exact sequence. If F is an injective F from, maybe I'll just use M to N. B is an injective R module homomorphism. Then what short exact sequence can you write?
0 M N 0 0.
0 M N
0 0.
0. But
So M mod N.
yeah,
M
so
mod N.
F need not be surjective, right? If it was surjective, then you could write 0 here. If you write 0 here, then that means the kernel is whole of N and the image may not be whole of N.
Right.
So you have what you can do is N mod.
So the image of M.
Image of F, yeah. Image of F. So this by definition is surjective, right? And so of course you can put a 0 here, but you have to check the exactness here, but that also is clear. So what is the kernel of this map, of this quotient map Q? It's precisely image of F, yeah, because you are quotienting out image of F. Kernel of the quotient map is precisely what you are quotienting it out by. And hence image of F is same as the kernel of Q. Okay, so this is indeed a short exact sequence. And you know what this object is called, yeah? What is this called?
Co-kernel.
Yeah, co-kernel of F. Okay. Good. So, and if F is an isomorphism, then this is, so F is an isomorphism. Sorry. Maybe I'll just write this first. F is an isomorphism. Maybe I should have written this first. M to N is an isomorphism if and only if So these are all if and only if, in fact. Yeah. So then, yeah. So maybe, yeah. So converse is also true. Okay. So if and only if 0 to m to n to 0 is exact. Yeah. Isomorphism precisely means the kernel is 0 and the map is surjective. And that is what exactness at M means. The kernel of F is precisely the image of the previous map, which is 0. And exactness as so F is injective, and surjective precisely means this. Yeah. So you can translate something being isomorphism in terms of short exact, in terms of exact sequences. So now let's just complete this example 2 picture. So if you are given an arbitrary map, F from M to N, some arbitrary R module homomorphism. So need not be injective, need not be surjective. Still, you can make out a exact sequence out of it. It won't be short exact. So here K is, you can take it to be kernel of F. So maybe I'll write it in words, yeah, instead of introducing notation. So kernel of F to M, there is a natural injective map, and that you can denote by putting a 0 here. And then you have a map F here, then N. Now F need not be surjective. To ensure that it's exact here, you have to, what you have to do is consider this map N mod image F, yeah, which is same as the co-kernel of F. Yeah, so maybe I'll write since I've written kernel there for symmetry, co-kernel of F. Yeah, co-kernel of F is same as N mod image F. Yeah, and then of course Q is a surjective map, so you can put a 0 here. So this is not a short exact sequence because it's not a 5-term sequence; it's a 6-term sequence. Yeah, but it is. Then you can say that this is exact. Okay. So this is what exact sequence look like. Any questions? Okay, it looks like I can't make it smaller. Okay. Okay, so I also wanted to talk about home and so on. So maybe it's a good time to stop. So I'll stop here, and I'll give one more talk on this homological kind of thing. So I'll talk about home functor and maybe projective modules next time, and then I'll see if there may be a talk about tensor product as well. Okay, so maybe I'll give 3 talks and we'll wrap it up with that. Okay, any questions? Okay, so let me stop.